In this video, I want to talk about probability versus statistics and the difference between these two things. It's about a question that I posed yesterday. There's a very simple rule of thumb. Probability is just more of a theoretical model. When you think of probabilities, you're thinking of a more abstract thing in mathematics. And when you think about statistics, you have to think that you're dealing with data, with something that came out of an experiment, that data that you gather through a survey or something like that. Okay, so that's basically the difference. Probability is something that it's in theory, and statistics has to do with something that you physically saw, that you experimentally obtained. Of course, this is highly idealized. Things get more complicated. Probability in turn can be used to predict things about the world, and statistics is used to actually come up with models, with mathematical abstract models for probability, and again say things about the world. So both kind of feedback to each other, give feedback to each other, and when we're describing real life processes, the difference gets blurry. Let's see how this works. Think of an example of rolling a die. Let's roll a die. So what's the probability of getting, let's say, 5 if we roll a die? If we think that this die is fair, and also we're thinking that this die is a common die, 6-faced, a cube, only one of these faces has the 5 on it, so you would have the 5 coming up just 1 out of 6 times, so the probability would be 1/6, about 16.6%. But this, again, is a probability. So we're basing our answer on a model. We're thinking of a regular fair die, 6-faced, shaped as a cube. This is theoretical. We don't have the die. We're not measuring the die. We're not doing anything. We're just thinking about it. So this is what probability is. But sometimes we can use probability to predict things, and things get a little bit messy there. For instance, this question: how many 5s would you get in 60 rolls of a single die? If we get a 5 just at the rate of 1 in 6 times, because we have it 1 in 6 in one of the 6 faces, then for 60 rolls we'd expect to get it 10 times, 60 times the probability of getting it. 60 times 1/6 is just 10. So we would expect to get 10 5s if we actually perform this experiment. I'm not doing it physically, but I went to a website called random.org, and there's a submenu called games, and you can actually simulate rolling a die. So I simulated it 60 times, and these are my results. You can count the 5s. Let's count the 5s. Here are all the 5s, and you can count them. You can see that there are exactly 10 5s, just as the theory predicted. So our original question, how many 5s will we get? 10, and that checks out with the experiment. But we could have asked the question about 6 or 3 or 4 or any number from 1 to 6, I mean, and the answer will still be the same. We just have 1/6 of a probability for getting any number, and in 60 rolls we would expect to see that number coming up 10 times. What about the 6 then? Here are all the 6s. If you count them, we don't have 10, we have 11. So what happened? These are the number on the die, and the second column marks the number of appearances, and you see that for 1 and 6 you have a discrepancy between the theory and the experiment. That sometimes happens when you're using probability models to say things about real life. Sometimes it checks out perfectly, sometimes it doesn't. And if you just look at this table, this, up to this point, is just statistics. This is gathering data. This is something you perform, an experiment you did, and the data that you gather. So if you can also use these statistics to try to approximate, to come up with a model. So you could ask yourself this kind of questions. What's the probability based on your observations of rolling a 1, a 3, or a 6? And the probability will be just how many times you saw a 1 coming up divided by the total number of times you've rolled the die. And the same for 3 and 6. And you get these probabilities: 15%, 16.67%, 18.33%. All of them are different, and the only one that checks with the assumed probability model of a fair die, 6-faced, cubic shaped, is the one for rolling a 3. Actually, for rolling a 2, 3, 4, 5, all of them check out. But then what happens with these other probabilities? Well, these ones are called experimental probabilities. I don't really like the name. It might confuse you, but this is something that we can also do. So we're basing our results on something that actually happened, on an experiment that we performed, and we came up with the model. So we went from real life gathered data to an abstract thing, to a model. But we have to put the label on it, say that it's experimental probability, to tell the reader that we're actually just counting stuff and trying to say that if maybe this is the trend. So here's where the blurriness comes in. Can we label that experimental probability as just probability? Maybe, maybe not. There is something called law of large numbers that says that the more times we perform an experiment, the closer we get to the actual probability, to the theoretical probability. So maybe, but not quite. How do we know that we have repeated this exercise enough times then to have confidence in our results, and what does it mean? Well, these are all things that we can actually study in theory for statistics to be helpful to answer these questions and to come up with probability models. So what I was saying at the beginning, that these two fields are separate, but sometimes they kind of give feedback to each other, is this. And the moral of the story is that probability is not the same as statistics, and that you can use them both to go from one direction to the other. You can use probability to predict things about the world, and you can use statistics to try to come up with underlying models for the probability. But going from the probability to an experimental situation is usually easier than inferring a probabilistic model from the statistics that you gather, from the data that you gather. Okay, so that's it.